Okay, good evening, guys. In this video, I'm going to discuss about unit number 4, RSM Response Surface Methodology Introduction. Most of the content in this presentation file are prepared from the textbook, chapter number 11, Design and Analysis of Experiment. Okay, so I would recommend all of you guys to please read the textbook so for better understanding. Okay. Assumptions of linearity in two-level design. So this basic introduction is much needed before we are moving to response surface methodology. So we studied in unit 2 about factorial design. So in factorial design, mostly either we can go with the 2 factor, 3 factor, 4 factor, 5 factors, like multiple factors. I hope you guys remember about what is meant by factor, and also its level, like 2 level, 3 level, like that. 2 level means 2 power 2, 3 level means 2 power 3. So the levels are represented with the k, that is what 2 power k here. So if we have 2 levels means 2 power 2. So for 2 power 2, in general, it is assumed like it is going to give us like a linear regression model. Like if one parameter and another parameter we change, output will be also influenced like that. So if we have a 2 power 2 design on the linear regression, in the sense, this is the linear regression model: beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 1 2 x1 x2. So here x1, x2 will be your factor 1 and 2, and beta 1 and beta 2 is coefficient for the factors. Beta 1, 2 will be your interaction effect of combining x1 and x2. So in general, in two-level factorial design, which is assumes linearity in the sense, as I said in the previous thing, this one assumes linearity. But in terms of real world applications, if we say, the linearity is very difficult to achieve due to various reasons. Various reasons in the sense with respect to design of experiment, in the sense noise factor or uncontrollable factors only. Okay, so the more the curvature or the non-linearity, the more will be error in the prediction of the interval. For example, from the previous slide equation, this equation, if we are predicting on model, we are making a model. This is the model. This is the model in this sense. In this model, if we want to find in midpoint what is the value, if we want to find any value in the midpoint by substituting the factor 1 and factor 2 value, then if that value, the response value coming here as a center point, in the sense the prediction model is working fine. If we are getting the response which is calculated from this predictive model, it goes somewhere here, in the sense what there are lots of gap between the initial prediction and originally what we are getting from the experiment. So in the sense, what does it mean? If this gap is more, in the sense more error, so in that case we can't able to use that linearity equation, or we can't able to claim it is linear. So then it will be considered as a non-linear. Where comes our response surface methodology will be useful. But we could be able to reduce this error. We could be able to reduce this error also. How? In the sense, instead of keeping the levels with a huge difference like -1 to +1, so huge difference in the sense you have to consider with our real-time examples, like if you are doing any machining using lathe machine or any conventional machine, if the spindle speed is rotating at 1000 rpm, consider as a level 1, 2000 rpm consider as a level 2, means a high level, low level, 1000 and 2000. For that, this model comes like this, means okay, if we could reduce this gap, instead of 1000 2000, if we could reduce between say for example 500 to 750, like that, if we are reducing, if this gap being reduced, maybe we could able to bring down this error percentages. But if we reducing that levels, instead of 1000 2002, 500 to 750, that also will affect the magnitude of the effect. Okay, so you wide range is not considered, so we can't able to adopt that model in multiple fields. So that is it's not at all right. So that's what I given here. Instead of 1000 2000, if we assume 500 to 750, maybe we could able to error percentage we can able to reduce, but magnitude of the effect will be minimized. So we it is better not to reduce that levels. So what else we can do in the sense, in experimental or industry persons, what they do, they will be considering a center point. So you know that this box, from this itself you can recollect, it's a 2 power 2 factorial design. Factor A in x-axis, factor B in y-axis. There are two levels for factor A, -1 and +1, that is low level, high level. And factor B also having the low level and high level, -1, +1. So four factorial points is available here. So experimental do consider the center point design. Center point design is the origin considered for this box, particularly it's a center point. So the purpose of adding a center point is to validate the assumption of linearity. So similar like a previous slide, this dot, center dot I given, same way it is given in the center point. The purpose of adding center point is to validate whether the model which we are proposing is linear or not. If the response at the center point, if we are substituting some value and finding the response as the output value is significantly different than the predicted value. For example, with the model we are predicting some value at the center point. Maybe center point means we know the x and y coordinates value. If we are finding that, if the value which we are predicting is significantly different from the straight line, it's like a huge error is there in the sense, then it is showing the non-linear behavior. So in that cases, if we want to reduce the error, we have to go with the RSM design or response surface design or response surface methodology. So this is the basic introduction about why we need to go for response surface design instead of factorial design. So few background. So main purpose of RSM design is RSM or response surface methodology is collection of mathematical and statistical technique. It's a combination or collection of mathematics and also statistical techniques are involved, which is useful to model and also to analyze the problems, in which our main purpose is the response of interest is influenced by many variables, will be affected by many variables. The main objective of RSM is to optimize the response. Okay, we need to increase or we need to reduce the error value or optimize the response. How we are going to optimize the response is the challenges available in front of us using RSM technique. So for considering two parameters here, like a chemical engineer is performing one experiment, in that he has two factors like a temperature and a pressure. With that he is making an equation like y equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus error percentage. So here how this error is influencing, how we could able to minimize the error by doing RSM methodology is main. So main objective of RSM is to optimize the responses value. Okay, and how it is different from factorial design. Basically, the response, the difference between the response surface equation and the equation for a factorial design is the addition of squared, mainly addition of squared or quadratic terms that let you model curvature in the response. So we need to provide curvature and predict that model. So adding squared term or quadratic terms in that equation will provide us the response design. That is the main difference between our factorial design and RSM design. So adding a squared term inside our regular model is RSM design. Okay. And also other way we can say that it RSM design, what are the assumption? RSM looks for quadratic or high order trends. Assume all variables are significant, all the variables like a factor 1, 2, 3, 4, all the factors are significant. Quadratic response always has a stationary point or a minimum or maximum or saddle point. Can be used as a optimization. Mainly it's for optimization purpose only. Okay. So this is just for response surface design. So here, if you consider, here is the peak. So here is the temperature, here is the volume of the room, and here is the efficiency, and it is represented as a 3D surface plot. So maybe the peak value in and around here. So what is exactly that value? Maybe we can able to get it from the RSM methodology. This is same representation that one is doom type, another one is the valley type. The same 3D plot can be represented in terms of contour plot. That also can be represented in terms of contour plot. Okay. Then, if this is the linear regression model, for example, this is the model 50 plus 10x1 plus 7x2, and it can be represented in terms of what to say, contour plot also. What does it mean in this contour plot? In the sense, for example, this is the response value 84, and here 4 is the x1 factor, and another 4 point something is also x2 factor. So along this line, throughout this line, the response value of 84 will be the same. For example, if I am taking here in this point, if I am taking, wait just a second. If I am taking a point here and here, for example, x1 is 2, x2 factor 2 also 2 in the sense, again it comes under 84. Similarly, if you consider 118 here and here, not only about this place as 118, here also it is considered as 118. The response will be equal. That is what linear regression model says about. Okay. So this one you guys need to remember. Then that RSM, as I said, the objective of RSM is to optimize the response. So you guys need to remember that it is to optimize the response. Its response value is the function of factor 1 and 2, function of x1 and x2 plus the error term or noise factors or uncontrollable factors. Okay, expected responses needs to be function of x1 and x2 only without having noise factor. That's why we are trying to do the RSM design. Okay, response surface will be function of x1 and x2 only without any adding any error term. Definitely error will be there, but non-significant or negligible amount of error could be acceptable for RSM design. And first order model for RSM design, y equal to beta 0 plus beta 1 x1 beta 2 x2 plus up to error. And the second order model, this is the second order model, will be represented in the 3D surface, beta 0 plus summation of I1 to k plus beta I xi plus xi square, like a adding squared term or quadratic term here will be giving us the second order model. And under that second order model or under the response surface methodology, it's a sequential procedure. We have to do a continuous process in order to obtain the optimal or better responses, or we can say optimal responses. RSM is a sequential procedure. We need to find which way, if we proceed, we will be getting better output, like finding the path of improvement towards the optimum. Finding path of improvement towards the optimum may be either way, either increasing trend or decreasing trend. Increasing trend in the sense we can call it as a maximizing condition, that is otherwise called as a climbing a hill or steepest ascent. What is maximizing? It's all about responses. What kind of responses we want to optimize. So again and again I am telling the same. If hardness in the sense we need to increase. If productivity means we need to increase. Efficiency means we need to increase. So what are all the depends on the parameter. We have to decide whether we need to go for maximizing or minimizing. Minimizing in the sense descending into a valley or steepest descent, but technique will be same. Either Direction of increment or decrement depends on the what kind of response, either maximizing or minimizing, steepest ascent or steepest descent. This is what mainly you have to, it depends on what kind of response value we are working on. Okay, for example, assume there is a operating condition. This is the current operating condition. It is given as the current operating condition as per that center point. Maybe you have all the coordinates where you have a different levels are there, high level, low level, like that for each factors. In this factor, with this combination, if you are running that responses, what we are getting in this range 65, in the sense 65 to 70 in between, then we need to change the sum of the parameters and see whether that response is increasing or decreasing. If this is, for example, increasing trend, it is given like efficiency I am considering as a, it's an increasing trend by changing some of the factors level value increasing, then this direction we need to consider, assuming that all this, for example, here response is 75, here is 80 throughout this. So perpendicular or with orthogonal to this, we need to move this. So once we reach some place, behind this point we can't able to move, or the response is not increasing, again it may trying to come back or reducing stages, in the sense we have to stop that particular is the optimal region. In that particular region, what is the operating condition or operating level, like a factor 1 and 2 operating level, that we can able to consider as a optimal parameter, which will be providing us the optimum responses. Okay, so if we consider, instead of efficiency, if I am thinking about surface roughness, in the sense lower the surface roughness is better, in the sense instead of going up like a steepest ascent, it may be going towards another direction by reducing it. Then moving towards this should be based on the step size. How much step size? For example, the current operating condition is the 10,10. If you want to increase or decrease, whatever, maybe if I am increasing, in the sense next level should be equally, we have to give like instead of 10,10, 12,12 operating condition we need to. Next step is 14,14, 16,16. The uniform interval we need to maintain. Or if it is the descent, like a steepest descent, instead of 10,10, it may be 8,8, 6,6, 4,4, like that we can go. So we should remember that the steepest ascent or descent, the interval needs to be uniform, and also the direction, once we decided, it will be moving perpendicular. So that is what the path of steepest ascent. That line through center of the region interest is normal to the fitted surface. It will be moving in this direction. See, the symbol is given like a normal or perpendicular. So this is the first order model. First order model will be beta 0 plus summation of I 1 to k beta I xi, depends on number of factors. We can able to increase the mathematical model further. Okay, the steps along the path are proportional to the regression coefficient. The steps along the path are proportional to the regression coefficient. The actual step size, how to decide the actual step size, is determined by the experimenter. Like us, only we have to, based on our previous knowledge, the process knowledge or other practical consideration, we have to decide the actual step size. Okay, the experiments are conducted along the path of steepest ascent until no further increase in response is observed. Okay, so until we find continuously, we have to do with the uniform step sizes. Where we are not getting any improvement in the responses, we have to stop that. So until no further increase in responses, we have to perform this RSM technique. So with that, I'm going to end the basic introduction about first order RSM. So in the coming video, we'll be checking about one example for RSM. Okay.